Hello everyone, welcome to this video. In this video, we'll be solving this question which states that if G is given to be an abelian group with identity E, right? We are given some group G. Within this group G, we have E as the identity. Let n be some fixed integer, then we have to prove that the set of all elements of G which satisfies this condition that x raised to power n is E, this forms a subgroup of G. Right, this is the first question. Now let's first of all focus on this question. So here we assume we are naming this set to be S such that it contains all the elements of the group G, where G is an abelian group, right? Such that we have this condition satisfied where n is some fixed integer, correct? X raised to power n is E. So we have to prove that S is a subgroup of this group G. So for subgroup, we first of all show that it is non-empty. So it should contain the identity element within it, right? So obviously you know the identity element satisfies this condition because e raised to power n is E. Hence E is definitely present in S. Hence the set S is non-empty, right? Next we consider two elements A and B present in the set S. So therefore we prove that AB inverse is also present in S, correct? So for that, because A is present in S, we have A raised to power n is E, and if we have B present in S, then we have B raised to power n is E, correct? Now we wanted to show AB inverse belongs to S. So for that, we need to prove that AB inverse raised to power n is also E. So let's consider the left hand side here. For the left hand side, you can write AB inverse raised to power n as AB inverse multiplied to itself n times, right? Now out of these n terms, what you can do, you can just make use of associative property to change the brackets here, right? So that you have one A here and one B inverse at the last, and in between you have the elements like this B inverse A, B inverse A, B up to B inverse A, up to how many times? In total n minus 1 times you have these B minus A. Now because your G is given to be abelian, hence you can write B inverse A as AB inverse. There is no issue. So writing B inverse A as AB inverse, B inverse A as AB inverse, and B inverse A as AB inverse n minus 1 times, you obtain, you see, you obtain A square here in the starting and B raised to power minus 2 at the end. So that now you can again make use of associative property to shift the bracket, so that now you have A square in the starting, B raised to power minus 2 in the beginning, in the last, and you are left with B inverse A, B inverse A, how many times now? N minus 2 times. So you can continue doing it like this, make use of this abelian property until you reach at a stage where you have A raised to power n minus 1 in the starting, B raised to power minus n minus 1 in the last, and in between you are left with just B minus A, B inverse A, right, which you, by the property of abelian commutative property, you can again write it like this, which becomes A raised to power n, B raised to power minus n. Now you can write it like this, B raised to power n raised to power minus 1. Now you know because A is present in S, so A raised to power n is E, and B is present in S, so B raised to power n is also E. So therefore you can write A raised to power n as E, B raised to power n as E, so that it becomes identity. Hence you have proved that AB inverse raised to power n is E. From here you see that this AB inverse is also present in your set. Therefore, by one step subgroup test, your subset S is now a subgroup of your group G, correct? Okay, moving forward, now let's see our second question. In the second part of this question, they are saying you to give an example of a group G in which the set of all elements of G which satisfies this equation. Now in our equation, n is given to be 2, right? If we take n is equal to 2, x square is equal to E, they are saying now it does not form a subgroup of G. Let's see how this is possible. So for this, let's consider some example here of group D4 such that you know it contains these 8 elements within it, correct? For these 8 elements here, it should be 270, correct? For the 8 elements here, we can construct a subset S such that it contain all the elements from D4 such that X square is identity, which is R0 in this case. So you see, you obtain R0 for only 6 elements here, because R0 into R0 is R0, R180 into R180 is R0, H into H is R0, V into V is R0, D into D is R0, then D dash into D dash is again R0. So you only have these 6 elements within your set S. Right, now we have to prove that this is not a subgroup. Clearly it is not a subgroup of D4. Why? Because this is not closed under the composition, under the group operation of D4. Why? Because if you compose H with the D, you get the result as R90, and R90 is not present in S. So therefore this is not closed, hence this is not a subgroup of D. Hence here we obtain a group D4 such that a set which consists of all the elements satisfying this condition does not form a subgroup of D4. Right, this is what was required. Now here you should notice one thing. Now you will be saying that we have proved the general result, but why then it is not working for n is equal to 2? It is because we have also skipped this condition of abelian group on G. Remember, D4 is a non-abelian group, right? So therefore we selected it to be an example here because it does not satisfy this abelian nature. Hence, you see, the abelian nature of the group is required for a subset consisting of elements which satisfies this equation to be a subgroup. Correct? So I hope you understood this question well. Well, that is it for this video. Thank you for watching.